Hola, hi, this is Al Nausdal, your statistics instructor. Let's get to work. Okay, in this short video, we will start talking about three special kinds of matrices. The first matrix we are going to be talking about is the inverse of A. Then we will talk about A transpose. Then we're going to introduce the identity matrix. And finally, at the end of this short video, we're going to use the inverse to solve a system of linear equations. Okay, so that's the plan. Let's begin with the inverse of A. First, an inverse is a property of a square matrix, meaning a matrix with the same number of rows and columns. Okay, so that's a square matrix. We will denote the inverse with a superscript of -1. Okay, so we're going to have something like this: A -1, and we're going to read it as A inverse or the inverse of A. Okay, so A inverse, A inverse or the inverse of A. And as I said a couple of minutes ago, we are going to be using at the end of this video A inverse to solve a system of linear equations. Okay, next topic, next item in our list, A transpose. When we transpose a matrix, we just exchange the columns and rows. That is, we turn the columns into rows and the rows into columns. That's it. So the new matrix is going to be designated with a prime or a superscript of T as follows. So A prime would be A transpose, or we could use this notation, A superscript T, and again that's just A transpose. Okay. Okay. How about we just do an example? Let's use R, okay, to find the transpose of a simple matrix. Let's define a matrix about one with 3 rows and 2 columns that looks like this. Just like before, we're going to be using the special command matrix and C, concatenate. And how about the first column vector is 1, 4, 5, and the second column vector is 2, 8, and 6. I said that I would like to create a matrix with 3 rows and 2 columns. Let's see what it looks like. Okay? So matrix formed by two column vectors, and each column vector has 3 elements in it. So if you want to find the transpose of matrix A using R, all you have to do is type T brackets and then the matrix of interest. There you are. So we did exactly what we said the transpose is doing, is turning rows into columns, right? Okay, good. So it's easy to find the transpose of a matrix using using R. Sorry. Now we are going to proceed to talk about the identity matrix. So the identity matrix is a square matrix. Again, a square matrix is a matrix with the same number of rows and columns. Okay. So the identity matrix is square, it's symmetric, and with ones on the main diagonal and zeros elsewhere. Okay? How about an example using R? Let's try and create an identity matrix, 4x4 identity matrix. How do we go about doing that? A very simple way of doing that is using a special command. So identity matrix, let me write it down here, what we mean by that. So, oops. Okay, let me create a 3x3 identity matrix. How's that? Because, you know, okay. Let's get rid of this one. I said initially that I would like to have a 4x4, right? Okay, so this is what we mean by a 4x4 identity matrix. That's what it looks like. But what if I wanted to create this matrix, identity matrix, 4x4 identity matrix, and we're going to have a special notation for this, a capital I, and just to be super clear, let's include the dimensions of our identity matrix. It's clearly a 4x4 identity matrix. Okay. Okay. So how do we create that 4x4 identity matrix? It's very simple. It turns out that R has a special command called diag. So diag brackets and then the number of rows or columns, since it's a square matrix, it's the same. There we are. Okay. Good. Great. So we have already talked a little bit about the inverse, how it's defined, notation, the transpose, and now the identity matrix. Now, before we continue, let me remind you about something we did in a previous video. We said that a matrix with a determinant of 0 is known as a singular matrix. Well, we need to be on the lookout for singular matrices because they cannot be inverted. Okay, we can't find the inverse of singular matrices. Later we will see that matrix inversion is a key component in linear regression. Okay, very soon we will see that. For now, let's use an inverse matrix to solve a system of linear equations. We talked about this system of linear equations before. Remember that we talked about determinants and Cramer's rule in another video? Well, we're going to be solving the same system of linear equations, but now with a different method, using the inverse matrix. Okay, so here we go. The system of linear equations, let me remind you that we solved back then, looked like this. There. Remember? Well, if you don't worry. I mean, we're just going to use it again to solve it using a different method, the inverse. So first, what we're going to be doing to solve this system of linear equations using the matrix inverse approach, our first step will be writing it using matrix notation. So, let's see, we have a 5 here, we have an 8, we have a 7, we have a 4, we have a 2 by 2 matrix then. Then we have a 2 by 1 matrix, or a vector if you will. And we have another vector here. Okay. Now let me use notation for these guys. We're going to use an X for that matrix there, X. And let me, just to be very specific, let me write down the dimensions of that matrix X. It's a 2 by 2 clearly. Now vector B, dimensions 2 by 1 equals vector, let me call this guy here minus 11 for y. I'm going to be using a y to refer to that 2 by 1 vector. Sorry, 2 by 1 vector. So as we can see, X and B are conformable, right? We have 2 columns here, 2 rows here, that's why we get to do this, right? And also we have the same kind of situation for X and Y. If you wanted to do the multiplication between X and Y, you could do that because the number of columns of X matches with the number of rows of y. Okay. Anyway, so once we set it up like that, we go, oh, or just like this. You go, oh, right. So just pre-multiply by the inverse of x, and there you are. That's all you need. That's going to be your solution. X inverse times y, and you're done, right? So that's all you need. So as I said, we already solved this problem using a different approach, which you can check later that both approaches give you the same answer. But now let's use R to find that solution. So just like before, we define our matrices first. So 5, 8, 7, and 4. We have 2 rows. We have 2 columns. The matrix y, or vector y, negative 11, 4. We have 2 rows, 1 column, right? And to find b, all we have to do is we need to find the inverse of the matrix X. Now let me, if you want just the inverse of X, all you have to do is use this special command, solve X, and that gives you the inverse of X. Okay? Okay. So now what we want is to find this guy, this unknown vector b, and that guy is given by solve x times y. But remember, if you want the matrix multiplication, you have to use this syntax, percentage star percentage, right? That's what R uses for matrix multiplication, right? Now we type the name of the object we just created, b, and if you check, you'll see that you end up with the same solution we ended up with using Kramer's rule. Great. Okay. But now we solved a system of linear equations where the number of unknowns and the number of equations, well, they are the same in this case, and that's why we got to use Kramer's rule, because remember that that's the restriction for this method, right? Because Kramer's rule uses determinants, and determinants are only defined for squared matrices, right? So anyway, what if we are dealing with similar problem, meaning a system of linear equations, but one where we have more equations than unknowns, right? So let me write that down. What if we had more equations than unknowns? Okay, so let's try and solve a particular problem that looks like that. Consider the following system of equations. About 4b1 plus 3b2 equals 92. So that's the first equation of our system of linear equations. 4b1 5b1, sorry, plus 2b2, that would be the next one, and then 8b1 plus 4b2 equals 144. So we have 3 equations and only 2 unknowns. So we can't use Cramer's rule or the inverse approach, because those work only when we're dealing with you know, square matrices. Because let me rewrite this using matrix notation. We have 3 rows, we have 2 columns, oops, only 2. No. That's better. Better. Okay. So we have 4, we have 5, we have 8, we have 3, we have 2, we have 4. And we have B1, we have B2, and we have 3 by 1 matrix here. Right? Okay, great. So we have something like this: xb equals y. But the problem is that this guy, right, I could write down the dimensions. So 3 by 2, this guy is going to be 2 by 1, so that's why we got to do this multiplication here, because x and b are conformable. But on the other hand, note that x and y are not conformable, meaning this guy, the number of columns, doesn't match with the number of rows here, so we can't, you know, we can't do that multiplication. And the thing is that the inverse of x doesn't exist, because it is not a square matrix, right? So how can we go about that? Well, what if we pre-multiply that equation xb equals y, what if we pre-multiplied by x transpose? So x transpose xb equals x transpose, oops, y, oops, lowercase, great. First, note that x transpose is going to be 2 by 3. Let's check that we can carry out that multiplication, that they are conformable. 2 by 3. Let me rewrite it. It's going to be, yeah, 2 by 3. That's going to be your transpose. Times x. X is going to be 3 by 2. And b, we know that works, right? But the thing is that x transpose that works. It's 2 by 3. And y is 3 by 1. So we can do that multiplication. Make sense? Okay. So, now think about x transpose x as a single matrix. Okay? Let me rewrite it here. X transpose x times b equals x transpose y. If you think about this matrix, if you think about this product as a matrix, if the inverse of x transpose x exists, then you're done. You have found B, the solution. So, provided that the inverse of this guy exists, B is going to be just this guy, the inverse of x transpose x times x transpose y. Right? Okay, so let's try and find the solution using R. Okay, here we go. Just like before, what we need to do is define our matrix, well, our matrices of interest, right? And then just do the products and finding the inverse. Okay, here we go. So X in this case is going to be the matrix with column vectors 4, 5, 8, 3, 2, and 4. The number of rows 3, number of columns 2. Let's make sure that it is the one we want. 4, 5, 8, 3, 2, 4. That's exactly what we want. The vector y is 92, 80, 144. Y (92, 80, 144). Number of rows 3, number of columns 1. Let's make sure it is the one we want. Okay, then our solution, right, will be given by this formula, right? X transpose X inverse times X transpose Y. Okay, so let me to make it easier, let me define a matrix called X star, which is going to be X transpose times, well, the product, you know, matrix multiplication, X. Okay, and then let me call Y star this product here, X transpose times Y. Okay, and that semicolon, if you leave that out, it's going to work. Just press enter and it's going to work. I do that because sometimes when you have multiple, when you're submitting multiple commands, you want to have that semicolon so R doesn't get confused. Anyway, so what we want is this guy, the inverse of this guy, solve X star times, or matrix product, Y star. The inverse times Y star. Okay. Another way of doing this is the following. Just type solve and then X star, comma, Y star. See? Same thing. Okay? So this is really cool, right? Let me summarize what we just did. Hey, we have a new problem, meaning a system of linear equations with more equations than unknowns. We had 3 rows and only 2 columns, meaning 3 linear equations and 2 unknowns, B1 and B2, right? So we couldn't use our Kramer's rule, we couldn't use our inverse approach method, right? But then we said, hey, how if we could turn it into a problem where we have a square matrix here, and then if the inverse exists, then we have the solution. And that's exactly what we did. By pre-multiplying by x transpose, provided that the inverse of x transpose x exists, we were able to find the solution for that system of linear equations. Make sense? Please remember this formula. This formula will play a very important role for us in this course in linear regression. That's a very important formula. We're going to see that it appears again and again in this course. Okay. So summarizing what we just did, today we introduced a few important matrices, the identity matrix, the inverse, the transpose of a matrix, and then using the inverse we were able to solve systems of linear equations. Okay, well, that's it for now. Thank you so much. Take care. Keep working hard. Bye. See you next time.